Welcome to refrigeration. We're going to talk about states of matter, specifically three states of matter: solid, liquid, and gas. For those chemistry and physics geeks, I'm not going to argue that there are 5 states of matter. On this side, Bose-Einstein condensates, and after vapors, plasmas. But in refrigeration, we're just working with solid, liquid, and gas, and we're going to look at the effects of pressure on temperature and boiling points and changes in state. So, for our example, we're using water. That's something that we're all familiar with, and because we're here in the U.S., we're using degrees Fahrenheit. If you were born somewhere else and your brain works in Celsius, get your conversion chart out, because we have to work in Fahrenheit. So, water exists as a solid all the way up to about 32 degrees Fahrenheit. At this point, it starts to make a change in state from solid to liquid. Below 32 degrees Fahrenheit, we have a solid water, ice. After 32 degrees Fahrenheit, we get liquid water. Water exists in its liquid state from 32 degrees Fahrenheit all the way up to 212 degrees Fahrenheit, where it will boil and become a gas or a vapor after 212 Fahrenheit. So those are the 3 states, and we have change at these 2 points: solid to liquid and liquid to vapor. Now what I want to point out is the change in these points, okay? Particularly the change in liquid to vapor and how pressure affects that. So I have a chart over here, and what we can see is a change in elevation. The numbers that we just looked at were sea level numbers. So the boiling point of water at 212 degrees Fahrenheit is at sea level. And the reason that sea level is important is because at sea level, atmospheric pressure is 14.7 psi. So that's the weight of the atmosphere above us. It's pressing down with 14.7 pounds of pressure per square inch. And as we go up in altitude, at 6,000 feet, the pressure is less. It's 11.8. Okay? So go find a mountain, climb up 6,000 feet, and you're going to find that atmospheric pressure has decreased. As atmospheric pressure has decreased, so has the boiling point of water. Now on the top of the mountain, if you're going to boil your water, it's going to happen a little bit earlier, 200 degrees Fahrenheit. If you go a little bit higher, you're not going to get this height on the East Coast, but go out to the Rockies and you can achieve 9,000 feet. Okay? Atmospheric pressure is a little bit lower, 10.5 psi. The boiling point of water has also dropped to 195 degrees Fahrenheit. Higher still, okay? In the continental U.S., I don't think you're going to get 17.5 unless you're in an airplane. Atmospheric pressure is lower all the way at 8.29, okay? Water is going to boil at 180 degrees Fahrenheit. So the important lesson here is that as pressure decreases, the boiling point of water also decreases. We're going to look at the other side of that too, because this is what applies to air conditioning. Remember, sea level 14.7 psi. We're all very familiar with that. That's what we're feeling right now. Water's boiling at 212 degrees Fahrenheit. If we increase pressure, okay, to 50 psi, the boiling point of water is going to happen around 281 degrees Fahrenheit. If we increase it even more, all the way up to 100 psi, we bring the boiling point of water up to 328 degrees Fahrenheit. So we see a dramatic change in the boiling point, or the point where liquid water is going to change into a gas, as pressure increases and as pressure decreases.